Hello, I am Dr. Xenia Worth. In this video, we will be discussing stress transformation equations and Moore's circle. First, we will define the stress transformation equations, and then we will graphically represent stress transformation using Moore's circle. The plane stress transformation equations allow you to define the stresses acting on a body at any angle theta from the horizontal, if you know the original stress state acting on the body. You have to be given an initial stress state, but if you have been given an initial stress state defined by two normal stresses and one shear stress, sigma x and sigma y are your normal stresses, and tau xy is your shear stress, then the stress transformation equations are the following. To find the normal stress on any plane rotated from the horizontal, you would use this first expression. And to define the shear stress on any plane rotated from the horizontal, you would use this second equation here, where this diagram represents your initial stress state, not rotated on any plane. As soon as you rotate that body in some direction, you are causing new stresses to develop, or you are feeling new stresses. So you are trying to determine what those new stresses are, both normal to the body and shearing the body on this new plane. You can also use these equations to determine the principal stresses and maximum shear stresses acting on a plane. The principal stresses are the maximum and minimum values of stress acting on a body. In the plane or on the plane where the principal stresses are occurring, the shear stress is 0. And these principal stresses are represented by the terminology sigma 1 for the major principal stress, the maximum stress, and sigma 3 for the minor principal stress. You can find the principal stresses using these versions of the plane transformation equations here. Given what you know about your initial stress state, you can find sigma 1 and sigma 3. You can also use your principal stresses or your initial stress state to determine the maximum shear stress acting on a body. That will act on a separate plane, but it will also be related to your initial stress state and related to your principal stresses. If I know my principal stresses, it becomes much easier to determine the normal and shear stresses acting on any plane because the equations become shorter. The equations are smaller because you don't have shear stress acting on this plane. So knowing my principal stresses, sigma 1 and sigma 3, the normal stress acting on any plane is represented by this equation here. And the shear stress represented on that same plane is represented by this equation here, since I have no contribution of shear stress on the principal stress plane. I can also use my initial stress state to determine the angle of both the principal stress plane and the maximum shear stress plane. These two planes will be at different angles from each other since they're representing different quantities. But the angle of the principal stress plane, where the shear stresses will be 0, is represented by this function here. It is a ratio between my initial shear stress and the difference between my initial normal stresses divided by 2. And then I can find the angle of my maximum shear stress plane as the angle of my principal stress plane minus 45 degrees. But I can also do all of that work graphically. So everything we've discussed so far has been looking at using equations to find my new quantities that I'm looking for. However, I can also use something called Moore's circle, which is a graphical representation of the stress state. It is a graphical representation of the transformation equations for plane stress, and it is a way to visualize every possible stress state acting on a body, given what you know of its initial stress state. This red circle here is Moore's circle, and it defines the various amounts of shear and normal stresses acting on a body. As the shear stress is changing, as the body is rotating, so is the normal stress, and you can find every possible combination of shear and normal stress states for that particular body. So you do have to make sure that when you are using Moore's circle, you are representing a single body. You are not representing every possible body at every possible stress state. You're representing a single body. Graphically, you plot the initial stress state on the tau sigma plane here. Tau is positive in the downward direction by convention, and sigma, your normal stress, is positive to the right. You plot your initial stress state given by sigma x, tau xy, and sigma y. And then you can use that to, one, find the angles of your principal and shear stress planes, find your maximum shear stress, find your principal stresses, and to find any possible combination of shear and normal stresses acting on that body. So let's look at an example problem. We're given an initial stress state here, defined by an initial normal stress in the x direction of 20 kPa, an initial normal stress in the y direction of 50 kPa, and an initial shear stress of 15 kPa. And it looks like this. Based on this initial stress state, determine the principal stresses, the maximum shear stresses, the angle of the principal stress plane, and the angle of the maximum shear stress plane. We can do this computationally using the stress transformation equation. So we're going to try that first. First, sigma 1, my major principal stress, is equal to sigma x plus sigma y over 2 plus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. So I can plug in what I know of my initial stress state. Sigma x was 20, sigma y was 50, and tau xy was 15, and determine computationally that the major principal stress is 56.21 kPa. I can do the same thing for my minor principal stress. The equation changes slightly because you have a negative here above or in front of the square root, but you use a similar procedure to get the answer of 13.79 kPa for my minor principal stress. I can also use either what I know of my principal stresses now or what I know of my initial stress state to determine my maximum shear stress acting on this body. And at some point, at some rotation of this body, my maximum shear stress is going to be 21.2 kPa. You can also solve for your angles of your principal and shear stress planes using the stress transformation equations. You still have your initial stress state defined. You plug in those values from your initial stress state. You take the arc tangent, divide by 2, and you find that the angle of the principal stress plane is 67.5 degrees. And the angle of the maximum shear stress plane, where the maximum shear stress is acting, is rotated 22.5 degrees from the horizontal, and that is the angle of the principal stress plane minus 45 degrees. However, you can also solve this problem and find all of these quantities using Moore's circle. So why don't we go ahead and try to do that? For that, we're going to open AutoCAD here, where we have just a simple XY axis here, the x-axis representing your normal stress plane and the y-axis representing your shear stress plane. And here is my initial stress state, 20, 50, and 15. So let's go ahead and start plotting on Moore's circle using AutoCAD. I'm going to create a series of lines here, define my initial stress points. First is 20 and 15. This is my initial point of my Moore's circle right here. Then I have another point defined as 50 is my other normal stress, initial normal stress value, and negative 15, which means 15 in the upwards direction here. So these 2 points define the outside of a circle, and I can come up here and define a 2-point circle using the AutoCAD features. First point, second point, and here is my Moore's circle now. Now, to define the maximum shear stress and the principal stresses, I simply look at where the circle crosses the axis. First, the circle is going to cross the x-axis at 2 points, and those 2 points are the locations of the minor principal stress and the major principal stress, sigma 3 and sigma 1, because this plane is where the shear stress is equal to 0. So I can use the dimension tool to actually dimension the length of those points and understand what those values are. Dimension 1, dimension tool, from 0 normal stress to the edge of my Moore's circle here. For my minor principal stress, I see that it is 13.79 kPa, the same value that I got using the plane stress transformation equations, but this time I did it graphically. For my major principal stress, which is where the circle crosses the x-axis on the opposing side, I see I got 56.21 kPa. So I got exactly the same answers using a different method of representing stresses. Now let's find our maximum shear stress. I'm going to create a line from here to here. You'll see why I needed to do that in a second. I'm going to start at the center of the circle, and I'm going to draw a line through the bottom. The maximum shear stress occurs where the circle has the highest y value. So the y-axis is here. So the highest y-axis either occurs along the bottom here, or it occurs along the top here. You will see the same value. This is essentially the radius of the circle. So I can dimension that as well. Maybe move this down a little bit. And I see that my maximum shear stress, or the highest point, the maximum value on the y-axis here from the origin, is 21.21 kPa. Again, the same value that we used, or the same value that we found using those equations. So now I have my maximum shear stress, my minor principal stress, and my major principal stress found using Morse circle. The last thing I can do is I can find the angle of the principal stress plane and the angle of the shear stress plane. I'm going to go ahead and delete one of these lines I just made because I don't need it anymore. And I need to create a new line from the origin to the edge of the circle as a reference point. And I can do an analysis, a dimensional analysis of the angles to determine the angle to the principal stress plane and an angle to the maximum shear stress plane. How do I do this? Firstly, if I look at this graphically, the x-axis represents the angle of the shear stress plane, or the location of the shear stress plane. Because on this x-axis, firstly, in order to find the angle of the principal stress plane, I recognize that this x-axis here, where the shear stress is equal to 0, is actually the location of the principal stress plane, because that is the definition of the principal stress plane. Shear stresses are equal to 0. So I need to find a way to dimension an angle from my initial stress state, defined by this line, these 2 points here at the edge of the circle, to the angle of that principal stress plane. I can use the dimension angle function to select first this initial line and this line. So I start with my initial data point here, my initial stress state, and I've rotated the body in such a way where I've hit the principal stress plane here, where the shear stresses are 0. And I see that that angle is 135 degrees. That is not the angle that I found using the plane stress transformation equations, because in my initial stress state here, you can see that sigma x and sigma y are 90 degrees from each other. However, when this stress state is represented on Morse circle, sigma x is here, sigma y is here, and these are now 180 degrees from each other. So just by virtue of plotting the initial stress state on a circle, I have gained an extra 90 degrees worth of rotation. So please keep in mind that this value, 135 degrees, is 2 times the angle of the principal stress plane. We can use the same approach to determine the angle of the maximum shear stress plane. The maximum shear stress happens here. The radius of the circle, it happens at the maximum value of shear stress, or the maximum point on the y-axis. I'm going to create a line from the origin through, and this line represents the actual location of the maximum shear stress plane. I'm going to dimension again from my initial stress point here, the line that represents my initial stress state, to the line that represents my maximum shear stress plane. 45 degrees. Again, this is going to be 2 times the actual angle of the maximum shear stress plane. because I'm representing two stresses that are in reality 90 degrees away from each other as a 180-degree line on this circle. So please keep in mind that you will also need to divide this by 2. Lastly, to conclude this video, I'll show you a short practice problem. I encourage you to do this problem in both ways. Now that we've solved that one using Moore's circle, I encourage you to go back and try this problem. I've given you 3 new stresses, new sigma x, sigma y, and tau xy values, and I encourage you to determine the principal stresses, the maximum shear stresses, the angle of the principal stress plane, and the angle of the maximum shear stress plane using both methods. Try doing this using the plane stress transformation equations, and also try doing this using Moore's circle graphically. You will practice through AutoCAD, and you will practice applying these equations in a graphical format. I hope you found this video useful for your class.